Alright, when we last visited this example with this composite post, we did all this work, the statically indeterminate, elastically based work. We had this compatibility equation, the force deformation relationship, that's what was the elastic part of it. And we found out that the wood yielded under this 180 kip load. And so, not the steel was elastic, pretty close to having yielded, but not quite. So, that's not so good in a lot of kinds of ways, that this system or this analysis results are not adequate, as they violate our assumption about elastic behavior. So what the heck do we do? Right? Well, there's this notion of full plastic behavior and partially plastic behavior, and most importantly, it's all based upon what's going on at the material level. And that's our constitutive behavior. That's just the stress-strain diagram for our material. So a lot of materials look an awful lot like a linear elastic region, and then we get into the yield region. It either looks like a flat plateau or it is close enough that we can model it that way, and we do. And so our yield stress becomes that limit. It's the same as the ultimate, and then there's our yield strain. And if we have that sort of elastic, perfectly plastic behavior, then the analysis actually becomes fairly easy. If it's not, then it still can be done. It just requires a little bit more effort, that perhaps you have to use some functional expression for this, where this is a really simple one. It's Hooke's law, and then it becomes flat. Otherwise, maybe not so much. Now, let's look at a global big picture of what just happened to us. If we were to draw a similar kind of diagram as a stress strain, but rather force displacement, the total force P, which the magnitude of it was 180, but let's let it be variable. And let's let it start at 0 and measure then how much this rigid cap displaces, then going downwards. That's delta of the cap. So that would be the system's force displacement relationship. And initially, that force displacement relationship would be linear elastic until one of the materials yields. That would be P sub y. Now, we just found out in the previous attempt at this that it was the wood that caused this to yield. Once the wood yields, it then goes out into the plastic region, has no stiffness. So the stiffness that's left over in the system is going to be that of the steel. And it will continue to accept some load, but the whole system will be a lot less stiff because you're not combining both materials. And at some point then we're going to get to the fully plastic region, and then it will flatten out. And because the materials have the ability to hang in there and continue to accept deformations without rupturing, or squeezing, compressing and rupturing, in a sense, crushing really, in this case because it's all in compression, we can continue to march out until at some point something really does completely rupture and it breaks down. And we would call then the corresponding displacements then our yield displacement. That'd be first yield. This would be our fully plastic displacement, and then maybe we can continue to go on out until actual rupture way out in here, some sort of crushing was the case. Now, our analysis before that said that we ended up with a 2.1 KSI stress in the wood, and that's greater than the yield, is ignoring this. It's pretending like this elastic curve for the system can continue to go on, right? And the slope of that would be the global stiffness, the original global stiffness. And so we were up in here, and anytime that we want a result that's somewhere else, all we have to do is follow this curve up and down. So it's just a proportionality kind of thing, right? So if we wanted to come up with, well, what's the force Py that is actually associated with first yield, we have to know which material yields. We know that, right? So I'm going to actually skip down to here below real quick. That, all right, the wood yields first, and it was, we know that when P equals 180 kips, the stress in the wood equaled 2.1 KSI. So then the question becomes, what does P equal when the stress in the wood is equal to 2 KSI? That's the yield stress of the wood. And it's just a simple proportionality, because then we're using linear elastic behavior. So we've already done one of the analyses. Heck, all we have to do is rescale this. And that means Py will equal the ratio of 2 over 2.1 times 180. So we really haven't gone too far over. And that's 171.4 kips. Right, so that's first yield. Anything in between here we have to figure out. But hey, you know, if we go find this right here, well, heck, then everything else in between is a straight line. So let's look at the Foley plastic. That means all materials have yielded. That means all materials have a stress that's equal to the yield stress. Now that doesn't mean the strain equals the yield strain, but we're out here somewhere and the stress doesn't increase with increasing strain. This makes it so easy to do the analysis, because we don't have to be concerned about what the deformations are, because the strain doesn't vary with, or rather the stress doesn't vary with the deformation or the strains. So sigma steel will equal the yield for steel, which was 36 KSI. For the wood, that would be equal to 2 KSI, 2000 PSI, but 2 KSI. And so when you go back to that free body diagram that we have from before, that's still valid. That never changes. Here, 100. We've got P coming down. We don't know what the magnitude of the P is, but we've got this whole system here. So this equation of equilibrium is the same, it's just that we don't know what the value of P will be. So we have 2N steel, because we chose to represent the force in the steel, only one steel plate, plus then that of the wood has to equal our Foley plastic load. And so that Foley plastic load for the steel is 2 times 36 KSI times the area of the steel. That's 1.5 square inches, right? 1/4 times 6 inches wide, right? And the 2 then is because we have 2 plates there, plus what we get from the wood. That's now 2 KSI times 6 times 6, so 36 square inches. That equals our PF Foley plastic. And so that will be 2 times 36 times 1.5, that's 108, plus 2 times 36, bam, 180 kips. So I kind of sucker punched you a little bit, I guess, in that when I applied the 180 kips to the system initially, I knew, because I'd already done the analysis, that we were already at the Foley plastic level, and that when we did the elastic analysis, we wouldn't get it right. Okay, so that's kind of interesting. Again, now if you go back, we can find what the delta Y is. We've kind of rescaled things. We can go calculate, now that we know what the system load is, we can recalculate the axial forces. And once we know the axial forces, we can find the stress. Once we know the stress, we can use Hooke's law to find the strain. Then we can find the axial deformation that's happening. And since the axial deformation in one of these is the same as the delta cap, bam, we got this one, right? Same kind of thing to work ourselves out to here, to get to the displacement associated for that, and any load, that applied load that's in between, we just use basic geometry to figure out what the displacements are and the state of the system of the various components are.